Good afternoon. Hopefully everyone's in a nice lunch coma and won't remember any of this. No. My name is Grant McAllister. I'm an actual engineer on the RDS team. I work mostly with Postgres these days, but I've had a hand in all of the RDS stuff, so happy to answer questions both about Aurora, RDS in general. The talk today is going to be a deep dive on Amazon Aurora Postgres. I should really put that up there. I think I deleted that. And we're going to dive into really trying to understand some of the reasons why this is different and why you'd care. When we first came out, we had marketing numbers that said, oh, we're faster and all this stuff. But that's only relevant if it actually is helpful for you. And so this talk is really to try to explain why, if you were looking at deciding, you might make choices. So we have an RDS Postgres universe, as I like to think of it, and that really comprises of RDS Postgres, which is the community Postgres, and Aurora Postgres. So from a client perspective, these things should be exactly the same. That's our goal, right? They're 100% compatible. So we have RDS Postgres there in the gray. It runs on top of EBS, standard block store, right? Things that we all are used to using. On the right, Aurora Postgres. Same head nodes, EC2, same kind of thing. But on the back end, we have Aurora storage. And I'll get into the details of why that's different in a bit. So from the two engines perspective, these things are all the same. So we both support 9.6 with the exact same extensions. Now, I will say that RDS Postgres has their 10 version out already. We're still coming out with that soon for Aurora Postgres, but those things will be the same in a little bit. We both have backup and recovery, point-in-time restore. They both have high availability and durability, although Aurora Postgres has slightly better language there. Security, secure by default. That's kind of one of our base things with RDS, is we want these to be secure by default. So these are the same from that perspective. Read replica support on both of these engines, cross-region snapshots. We do scale compute. And we also allow online scale storage. In the case of Aurora, that's auto scaling of storage. The two things that are kind of missing the major sort of features are we don't have cross-region replication yet for Aurora Postgres. That's one of the things that we're working on. And the other is outbound logical replication. So this is a feature that Postgres added in 9.4. It's based on wall logs. We don't do that with Aurora Postgres, so that's something we're adding back. The other thing is right now the smallest instance type we support on Aurora is an R4 large, which is quite a bit larger than the T-style instances that we support on RDS Postgres. But again, it's another thing that we're actively working to get to. So that's kind of just the high level of the two engines. Our goal is we're one team inside of AWS that supports the Postgres universe. So our goal is to make sure from a client perspective that this remains true, that you don't care. You write an application, you can connect to either of them. You're going to make the choice on the features and the performance stuff that I'm going to talk about next. So let's talk about the base architecture of Aurora. So in a lot of cases, this is the center setup for our regions. We have 3 availability zones, and I've just given them fake names there, inside of one region. Typically, you're going to have applications in one or more of these availability zones, and you want to talk to your database, which I've sort of noted here with the read-write thing, right? But that's just the EC2 head. So what's behind that? So for Aurora, we have this thing called Aurora storage. So this is spread across the 3 availability zones and has many servers. And so like the lighter sort of purple, each one of those you can kind of assume is a server, except for that we have hundreds or thousands, depending on which cluster you're in. And this is a highly distributed system. So what does this mean for you as someone that wants a database? Well, what we do is we spread these 10 gig chunks of your database out across these servers, right? And we make 6 copies, so 2 in each availability zones. And I've kind of tried to denote that with sort of the different colors showing you that, if you had a somewhat large database, it would be spread out in this manner, right? So when you go and you do a commit in Aurora Postgres, we're going to write a log record. And that's all we're going to write. We never write anything but log records, okay? That's going to flow down to this storage system, right? And it's going to get written to 6 places. Now, we use what's called 4 of 6 quorum. So we only need 4 of those to get done to say we're committed. And I'll show you why we did that in a little bit. Now, coming back, on the other hand, we read blocks. So this is standard Postgres, right? The block that gets read in is the exact same block format that is used today in Postgres. There's nothing different about it, right? And so when it gets back to that regular portion of the Postgres engine, everything else is the same, right? Now, the interesting thing is, remember how I said like we only write 4 of 6? Let's say this is one of the ones that we didn't actually get written, right? Well, we can repair those by copying from any of the other members in that group, right? And so we could do a repair from somewhere else. So if that one has a problem, we can repair it from one of its pairs, right? If a whole node in this storage system goes down, we don't have to copy all of those things to one specific place. We'll copy them out to various nodes, right? And we'll manage the hotspotting and the recovery. So we can do it like this, right? We can do different pieces, right? So we can copy and move them, and it's nicely distributed. So there's no single point of bottleneck. One of the things with a lot of storage systems that they used to have, if you had, a terabyte of storage in one part of a cabinet and it failed, you would have to copy that whole thing, right? This thing is copying like little chunks at a time. It can repair anything down to like the 8K block that you're writing from Postgres all the way up to a 10 gig segment, right? The other cool thing that's really different is we have read-only nodes, which we also call read replicas. I hate that name because it's kind of confusing. Because when I think of a replica, I think of copying the storage, right? I think of having a completely independent unit. That's not what we have here, right? As you see, what we have is something that connects to the storage, right? So you don't end up with extra copies of your storage. You just end up with, connecting to your Aurora storage for your cluster, right? And you can have many of them. So today we support up to 15 read-only nodes and 1 read-write node per cluster, right? And what I show here is that we actually do talk between the read-only and read-write nodes, and I'll get into the specifics of that, but it is a synchronous replication. So these are like a standard Postgres replica in that they'll be a little bit behind, but we typically are in sort of the 5 to 15 milliseconds behind, and we have a cleaner sort of profile, and I'll explain that as well in later slides. So the cool thing is, let's say a whole availability zone is down for some reason, power outage, storm, whatever. What we'll do is we'll fail over, and that would also happen if just your node fails, right? We'll fail over to one of your read-only nodes, and it gets promoted, and your application goes. And that's all done via CNAME, so your application doesn't have to really do anything. This all happens automatically. And we see times typically in sort of the 30 to 60 second range for a failover, right? This can be made a little faster if you don't use our DNS. The other cool thing is we support 16 terabytes in RDS today for most of our engines, but on Aurora we support 64 terabytes, so you can go quite a bit larger. For someone that started doing databases, 20 plus years ago, a 64 terabyte single relational database seems kind of insane, but I've come to terms with it because it is actually useful. We already have customers asking us for 256 terabyte databases for relational, not for reporting, and I'm like, wow, that's a lot of OLTP. So let's dig into what it really means to be a log-based system. So we don't have a log structured store, we have a log-based database storage base store, right? It's all about that we've moved part of the database into the storage, right? So I'm going to walk you through the difference between sort of how regular Postgres works and how Aurora works. So on regular Postgres, you have all these pieces of queued work, right? And what I mean there is that you have commits that are pending. Like you basically, 8 of your sessions have all said commit at once, and they're all ready to go, and they're waiting. So that when you say commit, they all can flow into the log buffer, right? And that's group commit, really cool feature that came along a long time ago. But the problem is that the next set of queued work from the other 8 sessions you had running are blocked. They cannot get into the log buffer now because the log buffer is getting ready to go to disk, which means there's a latch or a lightweight lock around it that prevents that. So that flows down, and that takes a little bit of time. Now, what's interesting is even if you do this to memory, this still happens, right? Like even if you have the world's fastest storage system, like you're just writing to the memory on your system, you still have this motion, right? So then once that happens, and you acknowledge that storage as done, you can say that's committed back to the clients, and the queued work can flow in. But you can see that there's this notion that there's these weights involved there, and the more work you do in this log buffer, the more time it takes to flush to storage, and the longer that latch is held. So that just is sort of a cycle that keeps going, right? So there's, making your log buffer bigger helps, but there's a point where it doesn't help anymore because it becomes about throughput, not about latency. So on Aurora, it's quite a bit different. As these transactions flow in, and I've just labeled them here just so that we can kind of keep track of them, But you imagine A, B, and these guys are flowing in. We just flow them down to storage as soon as we get them, right? So we keep track of the ordering of that they came in, so that would be the A, B, C, D, E, so we know like what the right ordering for the database is. But other than that, we send them to storage whenever we get them, right? So what's important though is we need to know if they're durable again, right? And we need to know that they're done in order. So here what we do is we have durability tracking, right? So in the durability tracking, we have basically a table that shows each of the transactions, right? And as they flow down, we keep track of that. So in this case, what I'm showing is transaction A has went to 2 places, transaction B is 2, right? And we're not going to acknowledge the commit back yet because we don't have 4 places. So once that happens, right, once A gets to 4, we'll return that commit back to the client. But you'll notice here that C is not being acknowledged, even though it has 4 of 6 quorum. And the reason is because of B, right? You'll see that B is at 3. And we want our database to be strictly ordered, right? So we have to wait for B to happen before C does. But once it does, we can acknowledge all of them. And you'll notice that like now E is at 5, and it's not acknowledged yet either, right? So in this way, we can have this, we no longer have a single point of contention on getting those commits out, right? The other thing that's different is how we write. So I'm going to walk through how full page writes work in Postgres and how generally checkpointing and all that works. So you have a block in memory. You go do an update. With the MVCC mechanism that Postgres uses, you basically end up deleting the old tuple and inserting a new one, right? So that's why you get like these 2 things happening, right? And you'll also notice we end up with a full block in the wall stream. And I'll explain why in a second. Now, if we do another change, we don't end up with one. So what's going on here? Well, the full block is only put into the wall the first time you touch a block after a checkpoint, right? So you can touch a block like 100 times after the checkpoint. Only the first time you get the full page writes. And of course, we have to checkpoint this block out at some point, a checkpoint interval. And then we also have to archive the wall out, right? Now, the reason why we do the full page writes is because on most operating systems, the block size that the database is writing at and the block size that the file system and at the OS is using is not the same. And that's the case like if you're using Linux here. We have 4K blocks in Linux, and we have 8K blocks in Postgres. So when we do that checkpoint, we're actually writing 2 things. And if the box crashes right in the middle of that, guess what? You only got half of it. And you're going to have corruption. And you're not even going to know you have corruption. So Postgres, a long time ago, added this ability, right, so that full page writes are on, which is why you should never turn them off in most cases, because once you crash, when you come back up, what Postgres is going to do is it's going to recover via the wall, and it's going to see that full page write, and it's going to go throw that onto the storage and basically fix up that mistake that was made by losing one of those 4K blocks. So this works really well, but it's kind of expensive, right? So now I'm going to show side-by-side comparison. So I'll flip through the Postgres side really quickly because we just showed that. I'll also show the one other thing that, of course, you have to archive all of the changes. And we back up the data files, and we also archive them to S3, right? That's part of our point in time. So that's all the writing we do, right? On Aurora Postgres, on the right side, we do that same update. We get those same 2 log vectors, right? Those get set to Aurora storage. And they're continuously being pulled to S3, right? So you don't even have to wait for a wall to be archived to get a backup here, like of the stream, right? So there's less data loss from a perspective of if there was ABRL and any time that you needed to do that. If you do another update or another insert, it's basically all just going to Aurora storage. So you can see fundamentally how much difference there is in the system. There's no checkpoint, there's no FPW, right? So this results in a dramatic difference in the amount of work being done by the system, right? So one of the other areas that you see a lot of full page writes is because of random values, right? So if you're inserting into a B tree with a random value or, for example, a GUID, what you're going to see is that you're going to do these inserts like 124, right? And that's going to flow through the tree, right, and touch a bunch of blocks, right? And in this case, it probably updates the final leaf node, right, in Postgres. Now, if you do another one, you're going to have another chunk of the B tree getting touched, right, and another leaf node being updated, right? And this continues. So if you just keep doing this, right, you will see that you get a lot of full page writes because the chances are these are all random pages you're touching in that B tree, right? So this is quite bad. To kind of demonstrate this, I built a really quick test where I just have this table that I created that has 9 columns, right? It has a whole bunch of random ones, like these, like the first PK that's a UUID. I have some right-leaning, like the timestamp and this sequence, but a lot of it's random, right? Just to kind of show that. And then I indexed every column. This is not typical, right? Most people don't have a 9-column table with 9 indexes. But most people do have 100+ column tables with 9 indexes, right? So this is just to show that it's not about the size of the table that really matters, it's really about the number of indexes. So when we go run this, here's what we saw. So this is kind of a little bit of a busy chart, so I'll spend a second on it. So vertical axis is inserts per second, right, to that table. And then I run this for a whole bunch of time, 300 minutes, right? And the red is the base. So this is RDS with its stock parameters, no tuning done. And what we see is we get really good performance for a tiny bit of time, 25,000 plus inserts per second, and then it drops. And this is because the workload keeps getting larger, right? So the working set size gets larger and larger. All those random indexes, they get touched. They do more full page writes, right? So what I did in the green was I said, well, I'm going to increase the time between checkpoints by making the wall size bigger. So that helps. We get a better result, you know, still beats the other one quite a bit. And then the blue line is Aurora, right? Because we have no full page writes, we have no checkpoints. So we get dramatically more stable performance. Now, I did a talk yesterday where I show you can do a lot of tuning on Postgres. You can get very close to that blue line, but you have to remove some of these indexes. You have to make them less random. There's ways to do it, so it's not impossible, but it just shows you kind of the difference that you don't have to make that choice with Aurora. I did the same thing with the update. Same workload, an update here on this one random, the Boolean, and then an update on the timestamp, right? And you know, just to show you that this isn't an insert-only kind of problem. And here we see the exact same graph. TPS, larger is better again on the vertical axis, the red being stock RDS, the green being me increasing checkpoint intervals, basically, and the brown being what we get with Aurora. So we're seeing we're getting like 4 to 5 times the performance here with doing essentially no tuning, right? And maybe, you know, 3 times over a tuned system. So what does this mean for you from an actual running your system? Because everyone's like, well, I don't necessarily care about getting the absolute maximum performance out. But there are other trade-offs, right? So one of the big things about Aurora is because we don't do checkpoints, we never have to do recovery. Because we're constantly taking those log vectors in storage and combining them with the blocks and doing basically recovery on the fly continuously in a distributed thing across all those storage nodes. So when Aurora crashes and comes back up, it's already recovered, right? So on this graph, I have the recovery time in seconds as the vertical axis, right? So you would like your recovery time to be shorter, right? Your boss doesn't want your database down, right? And the horizontal axis is throughput as far as writes per second. Obviously, you want more, right? With the same amount of equipment. So what I did to do this was I ran a workload where I ramped up the number of connections as I went. And so the first one you see is essentially with a few connections, I'm getting 3 gig of redo between the checkpoints. And recovery was taking about 19 seconds for that, right? And we're getting almost 20,000 writes per second. It's pretty good. But when we start pushing the system more with more connections, we now go to 3 times the amount of redo. But notice what recovery does. Recovery also jumps up by like more than double, right? And when we really push the system, we start generating a lot of redo, right? Like 30 gig of redo between the checkpoints. And that recovery is now taking 2 minutes, right? And you'll notice that slant on that, right? That's not a great slant because you can see where we're going. If I just keep pushing harder, it's going to just keep like going, almost straight up, right? You're going to just be generating more and more redo for very little increase in the amount of throughput you're getting. Now you'll notice, can you see that tiny little dot out there on the far end? I'll highlight it for you. So that's Aurora, right? So Aurora gets much better performance, right? We're talking about, this is 2 to 3x the performance, and the recovery time is about 3 seconds, right? So you no longer have to make a trade-off of would you like to write heavily or would you like fast recovery, right? So, and again, you can tune Postgres to have low recovery, but you're going to be down here, somewhere in your writes per second. So let's talk about durability, because this is one of the important features that we have and why we do a 4 of 6 quorum. So when we started with RDS, we did EBS, and EBS basically has 2 copies behind the scenes when you get a volume, right? In an AZ. When we did our multi-AZ product, we basically mirrored across those 2, so we had 2 locations, 2 AZs, 4 copies on disk, right? And someone said, well, why not have, 3 locations and 6 total copies, right? Because that'll be more durable, it'll survive better, it'll be more highly available. So we went and said, well, let's go look at that. And this is to sort of illustrate if you're writing to those like 6 locations, or those 3 locations and 6 copies, what's going to happen, right? You're going to send out those requests to be done. They're going to start, coming back, being written locally. And there's a lot of jitter because there's a difference in locations, right? For network, there's how fast those servers are. They're doing the storage, and so there's a lot of like variance, right? And what we found was, okay, so you have to wait for all of these to happen before you can say you're done, right? And what does this turn into when you actually run a test, right? So we did exactly that. We compared the latency in milliseconds for IOs with a synchronous replica, where we had in blue 2 AZs with 4 copies on disk, and then a 3 AZ, like 3 node, 6 copy on disk, right? And we're looking at the percentiles on the bottom, right? So basically, if you want to say the 50th percentile is kind of the average of what you'd see for your IOs. And we were seeing, 6 milliseconds for the one and 7 for the other. And you'd say, that seems fine. Let's go ahead and have an extra copy, right? That's not that bad. But the problem is when you get up to the 4/9 percentile, which is 1 in 10,000, but you see a jump from 31 milliseconds to 123. Now, remember when we think back to my illustration of the log buffer and waiting on it, right? And that nobody else can do work while you're waiting? Can you imagine that the log buffer has to wait for 123 milliseconds instead of 31? And how much work is going to get queued up behind that, and how much jitter you're going to throw into your database system, right? So we said, no, we're not going to give this to our customers because our customers are going to be like, this is more expensive and it's way worse, right? I don't like the performance. So that's where some of the Aurora stuff came from. What we do now with Aurora is we have those 3 locations and we send out these 6 writes, and then when they come back, we start getting them back, and then once we have 4, we're good, right? We still try to write to all 6 places, but the other ones we don't care about getting done before we can acknowledge, right? And part of this is that we're not doing this on a disk basis, right? We're doing this on a block basis. So we don't have to say, oh, well, that disk is stale because it didn't acknowledge a write, and so therefore you can't continue writing to that disk. What this means is you can't continue writing to that block on that storage node, but it's one block, right? And it'll catch up, or it'll get self-repaired. You're not doing these really large repair actions, you're doing these very granular ones, right? So this results in quite a bit different latency. So what I'm showing here is us running sysbench, right? And this is the P95 of the response time. So this is sort of the tail, like the higher end of the response, but it's a 30 gig working set, or 30 gig sysbench with 1,024 clients. Response time on the vertical axis, and then just minutes along the bottom that we were running. And the yellow is Aurora, and the blue is Postgres. And the thing I want to show you about the blue is single AZ. So this is not even multi-AZ, right? This is writing just to the local AZ, right? Versus this one is writing to 3 AZs. And what you notice is our time is actually more predictable, right? It's faster. Even if it was the same, I would be fine with this. But the fact is that it's not only more consistent and faster. Now, how many people can guess at what this sort of thing is? What do people think that is? That's checkpointing, right? So every time you need to checkpoint with Postgres, right, you're going to do a whole bunch of I/O that you weren't doing. So at this like little tiny point where they're doing really well, it's like, oh, the system's like, I'm the only guy doing it, I'm just writing the logs. This is working great. And then all of a sudden the checkpointer kicks in and starts working really hard. The amount of I/O going to the system goes up, your latency and jitter goes crazy, and now all of a sudden you're up here at 4 times the latency, right? So this is really going to throw your application off. So again, what we're trying to show here is that you can have a durable system that writes to a lot of places and still has very consistent performance, right? So let's talk about replicas and clones. I always joke that this sounds like a Star Wars reference, but it's not. It's about Aurora. So in Postgres, when you ask for a replica, we have your standard RDS Postgres on EBS, and we take a snapshot for you, we restore that snapshot, make another EBS volume. It's pretty standard. It's what you do too, probably. We get rid of that snapshot, and we fire up a read-only node. Now, this takes a little while because let's say you have 6 terabytes or 10 terabytes. We have to take the backup. Now, it's a differential incremental, so we don't have to take it all, but you might have written like a terabyte since we last took a backup, right? So we have to write that terabyte down to the S3, and then we have to start up an EBS volume and do all that, right? That takes a bit of time. So you have some catch-up time where you're replicating, but you're just catching up because you're so far behind that the replica is like not useful because it could be a couple hours behind. So it finally catches up, and now you're kind of good. You could say, I can start using this. So if someone does an update on your replica, it's going to write to EBS and read it back, right? Acknowledge it back, sorry, is what I meant. And then at that point, the asynchronous replication is happening across to the RO node, right? And we might have to actually read that block, right? Because that block might not have been in memory. So we might do a read to EBS, return that, and then we have to write out the changed block back to EBS, right? So this all takes a little bit of time. Aurora is completely different here. On Aurora, we still have that read-write node, but now we have this storage system that is a cluster, right? It's for all the nodes. So when you want a read-only node, you essentially attach a read-only node. This takes a number of minutes. You want another one? It's another couple minutes. Because we're not copying the storage, right? We're just attaching to it. And it's also different about when an update comes in, right? When an update comes in, we have to write it to Aurora storage, and that's it, right? We don't have to write it on the read-only node because the read-only node has access, right? It can read it. Now, but there is a problem here because let's say you have that update of that blocks in memory on the read-only node. Well, you'd have a problem, right? Because if someone comes in and reads that, they're going to be reading an incorrect version. So what we need to do is we need to flow over via asynchronous replication the changes, right? But the cool piece is we only have to update things that are in memory. Anything that's not in memory, we don't have to touch because we know it's already in the storage. It's all good. So to illustrate that, I ran PG benchmark against these two systems, right? So PG bench has 4 tables that it touches. You can see the accounts, tellers, branches, and history. The first 3 you load up, and then the history table gets created as you run, right? So the read-write, if you run it in read-write mode, you touch all 4 of those tables. If you run it in read-only mode, which I'm showing here, you only read the accounts table. You don't read any of the other tables. I don't know why they chose that. TPCC benchmark from I think 1922 or something. Not super relevant, but it is the standard Postgres benchmark. So when you do standard Postgres replication with their async replication and apply, you have to apply all those changes to all 4 of those tables, right? So you have to load them all in memory. So if you're using this, you're basically flowing through all these changes. And that works okay, but there are scenarios where that's really bad, and I'll show you that. So on Aurora Postgres, it's completely different, right? We basically do our asynchronous replication and only memory update, right? So essentially, we never do anything here, right? We never load those into the machine, right? So there's no extra work going on. It means your apply leg can be much better, especially in situations where you do backfills or any large chunks of change that you don't actually care about on your read-only node. So let's look at that, right? So the replicas, let's do a backfill on top of RDS Postgres running with a replica. So here I'm running PG bench with 8,000 TPS on our primary node, right? So this is a pretty good workload. And on the read-only node, I'm running 200,000 TPS on the replica. Those are single reads, so it's not quite as impressive. But the vertical axis here, they're a little hard to see. Sorry about that. But this line here, which is sort of orange on mine, and I don't know what color it is for you guys, is the number of writes per second being done on the replica. The blue line is the number of reads being done on the replica, and this funny line here in green is the replication delay. What's interesting is our replication delay on all the standard RDS products is measured in seconds, because when I started this silly thing, we first worked on MySQL, and MySQL had replication legs that were always in seconds. So we were like, hey, that's what the counter should be in. Turns out when you build a system that doesn't take that long, it's not so good. So you just sit there at 0, which means you're actually somewhere between 0 and 1 second of lag. I'm still getting our engineers to fix this so that all of our stuff will be milliseconds soon, because things have gotten much better since MySQL 5.1. But anyway, so we're going along, we're fine, right? This is what you'd want to see if you're running a replica. It's like, okay, it's basically okay for Postgres. And then I did a backfill on pgbench history. What did I do here? I said, basically update pgbench history, set, column whatever, set, X to, 16, no where clause, So just backfilled the whole thing, right? So this is a pretty horrible thing, but, it's something as a DBA that people have to do sometimes. They get, things where they're like, oh, by the way, we're adding a new column, I want you to backfill it, right? Nobody cares about all those rows, right? But you have to backfill it, and you have to do it in a way where you're like not destroying stuff. And here's what happens on Postgres, right? Our replication delay went up by 30 seconds every 60 seconds we were running, right? And if you actually look at this, this is quite a long time that I was running. Like this is a long, a lot of time. It just kept going up, right? The other thing you notice is that the write that we could do went down, right? Because we're doing way more work. And then the other thing is, after a while, this blue line comes up. Why does the blue line come up? Because now we have to start bringing stuff from disk into memory because we're updating a whole bunch of rows that we didn't actually have in cache, right? And guess what? I don't know if you can quite see, but right around then, this line actually gets more steep. We're now losing 40 seconds for every 60 seconds. So this actually went from being horrible to like horrific. And at this point, you're like, there's nothing you could do if you ran this backfill. You're basically just toast, right? You have to just wait for it to be swallowed. I really got to throw in that animation of like, the snake eating the watermelon, because that's essentially what's going on here, right? It's just got to get through the system. There's, nothing you can do. So let's look at what Aurora does. So same basic graph, except for I screwed up and I reversed the axes somehow. This is always fun when you're making presentations and don't notice this until you're giving it the first time. The major thing to notice is that the latency now is in milliseconds. And so this number is basically, I'm not sure if you can see that, but it's like about 0 to 15, okay? And we do the exact same backfill. Now, and the green line again is the latency, right? There is no writes because we're on Aurora, right? And there's a few reads, like I think it's 3 or something. So would anyone have been able to spot when I did the backfill if I wouldn't have put that big red arrow there? No, right? Because there really is almost no change, right? Because we don't have to do anything. We got to be able to say, no one's reading pgbench history, throw all those things away, right? This means you get very, very stable replica performance, right? Much more so than on a standard system. The other really cool feature that we just launched last month, that we announced at reInvent, but then didn't actually ship for a while due to some test issues, it was not actually an actual problem, was fast clones. So let's go back and we have our standard 3AZ storage, we have our read-write node, we have our application, we can set up our read-only nodes, right? But let's say a developer comes into you and says, look, I really need to do some tests against the data, the current production data. And you say, well, yeah, but I got like 10T or 20T or 60T in that database. I don't want to give you a copy of that data. That's going to be super expensive, right, to spin you up something to do that, right? What you used to tell developers is you just say, hey, go create a blank schema and go create some goofy data and see if you can make it work, right? But now what you can do is you can do a fast clone. And what is a fast clone? So a fast clone is we basically fire up another node, and this is like at a specific point in time. We basically do that, and we create another set of storage for you, right? So this guy is its own RDS Aurora cluster, so it's got its own storage attached to it. But notice that it's got none of these blocks in it that I'm showing as data, right? It's essentially empty. What it's doing is it's pointing at all the blocks in the primary storage. So until you actually make a change, so like if you go do an update on this guy, which you can do, then what happens is we will make a clone of that block. So it's copy on write. Anyone that's familiar with any of the copy on write file systems, this is sort of the same thing, but at a database level, right? And so what's really cool is you can also use this for reporting, right? Let's say you have a reporting job where you want to build a bunch of indexes that you don't want to keep around, right? Because guess what? Remember I was saying how more indexes can be kind of bad? Now, not as much on Aurora, but just in general, they're expensive, right? You could spin up a reporting clone at night, build some indexes, run them, throw it away, right? You can give all your developers a clone to work off of instead of individual test instances, right? With full copies of the prod data, assuming that's okay with your compliance people and all that fun stuff. But yeah, this is a really exciting feature, and this really shows you the power of Aurora, that we're going to keep incrementing on things, that this is a storage-based addition to our stuff. So this was great as a member of sort of more of the engine team. We didn't have to do anything here, right? This is like free lunch for us. This is a feature that was developed as part of the general Aurora storage system. Caching, on the other hand, we had to do some work on, and I'll explain why. So Postgres is very interesting in that it's the only database I've ever worked with that uses the file system page cache as part of its buffering solution. So when we set up RDS Postgres, we sort of allocate about 25% of the memory on the system for Postgres processes and OS processes, and this includes sorting and all those other stuff. We do configure a quarter as shared buffers, i.e. the Postgres buffer cache, and then the rest of it, about 50%, as the Linux page cache, right? And this is sort of, okay. When you go and do a read inside of Postgres and it says, I need that block to satisfy a query, it's going to go check for it in the shared buffers, and if it's not there, it's going to go ask for it basically from the disk, which will look in the page cache, and if it doesn't find there, it'll get it from EBS and go all the way back, right? So there's either 1, 2, or sort of 3 hops to get your data. This works pretty well, except for one of the problems is that you end up with this duplicate buffers, right? So most of the buffers that are going to be in your shared buffers will have just been loaded out of your page cache, so will be in both. Now, it's not a perfect overlap, so it's probably not actually 25%, but it's a lot more than 2 or 3%. It's probably closer to the 20s, right? This is quite different on Aurora because we don't have a file system. We talk to Aurora storage. So, it's not even in sort of the same area. So we have 3/4 of it in shared buffers because there's no real reason not to, right? So when we select, we basically go look at shared buffers. And if it's not there, we go get it from our storage, right? So less hops. One of the cool things with Postgres is when Postgres dies, the shared buffers die, but the Linux page cache survives. So you still have your data cached, right? Which is really handy. You're happy because your application's fast. Well, we don't have a Linux page cache, so we had to go build something that did the exact same stuff, right? So we built something called survivable buffer cache, which essentially does the exact same thing. When the Postgres processes die, our shared buffers stay there. We do the right level of invalidation to make it all correct. So to show kind of the effect of this, I ran another benchmark, PG bench read only, very, very large scale, 22,000. So this is 350 gig working set, right? And transactions on the vertical axis, higher is better. So with Aurora at 75% cache, we get nearly 700,000 reads per second, which is pretty impressive. We went and ran this on RDS Postgres, and we got quite a reduction, right? We only got 417,000. That's not very good. And I was like, what's going on here? As it turns out, we were doing 18,000 read IOPS. And the reason is that 350 gig, remember, we're not actually getting the whole cache on this 488 gig machine because some of it's being double buffered between the shared buffers and the page cache. So because of that, we end up doing some reads. So I said, well, let's go and reduce the shared buffers to 10% so there's more page cache so it all fits in. So I did that, and then I got a lower number. And I was like, what's going on here? And the reason why I got a lower number is that double buffering of doing that extra step of having to walk through the 2 page caches and all the extra system calls burns CPU, right? And we're doing a flat out run as fast as we can. And what you see is that overhead is actually material, right? That we're now at half basically the performance. And now this is read only, and this is very highly cached workload, so it's very specific, but it does show you the overhead of double caching. And just to prove you there's no monkey business, here's RDS Postgres with a 75% shared buffers that gives you almost the exact same number as the Aurora one, right? But of course, this is not a survivable cache, right? So you kind of have to make that choice. Like, do you want to be here with a survivable cache on Postgres, or do you want to be here and get survivable cache as well? We also made a bunch of changes in vacuuming. I'm going to skip through this pretty quick because I'm a little behind. This is why vacuuming matters, which most people know. That if you vacuum, you end up with free space, which ends up allowing you to reuse your blocks. If you don't, you end up using more blocks because you end up leaving the old stuff behind, right? That's pretty common. The more blocks you have, the more cache misses you have, the more non-hot updates you have, and in the case of Postgres, the more FPWs. This doesn't apply to RDS. And so obviously, when you run vacuum, if you don't run vacuum, you end up slowly trailing down, which is what this benchmark shows. You'd really like to be at the red line. This was only run for a half a day. If you continue to run without vacuum, that's that problem. There's also the problem of transaction wraparound. Now, one of the problems I was thinking about when we started working on this was I was like, well, look, we write 3 times faster. If we vacuum at the exact same speed of RDS Postgres, is this problem going to happen even if people have vacuum turned on? Yes, right? Is transaction ID wraparound a real distinct threat or more of a distinct threat? Yes. So we did some optimizations. One of the first ones that we've worked on is intelligent vacuum prefetch. So Postgres actually has a feature that they added in 9.6 called freeze maps, where they now know where, when they need to freeze stuff for transaction wraparound, where to go. And I've illustrated sort of the grayish, light-colored boxes as ones that need to be frozen, right? The green ones are fine. They're already good. So here's what you'd think Postgres would do for reads, right? But it's using the file system. And they did an optimization back probably on spinning media and said, if those blocks are within 32 of each other, then to get read ahead to work on the operating system, let's just read them all. And so what it actually does is do this. So if it's a big enough thing, you'll see it skips, but otherwise it reads a lot. So it's good because you have prefetch running, but it's bad because you're sending a ton of I/O that you actually don't care about back to Postgres, right? You basically read it into the engine to be like, oh, I don't actually need to do anything. What we do is different. We grab the individual addresses of the blocks shown in blue. We grab those together, and we submit one batch I/O. So up to 256 IOPS, it's all good, right? And that really makes a dramatic difference. In Postgres, this takes about 402 seconds. In Aurora Postgres, this takes 163 seconds. So that's a material difference, right? And because of that, because we don't have the FPWs and a bunch of other stuff, we can set vacuum to be much more aggressive. I'm actually going to skip through, I think, the vacuuming in memory portion. I've covered it in my other talk. It's just an interesting idea that we came up with, and I'll just skip through all this, but the main thing to realize, come on, there we go. So for vacuuming in memory, you can do this vacuuming in memory because you can set on Postgres, you can set per table vacuum settings, but with regular Postgres, you actually have to change checkpoint timeouts, and you actually have to do a lot of funny stuff. The cool thing with us is we have no checkpoints, right? So a lot of these things become irrelevant, and you can actually get better performance by doing this technique of being faster on your vacuuming without actually worrying about it. So I want to talk a little bit about monitoring performance. So as part of RDS or Aurora Postgres, we're in preview with Performance Insights. So this is a really cool tool that we're going to be rolling out to all the engines here shortly. This literally allows you to dig into what's going on with the SQL on your engines. And again, one of the things that we did was we backported some of the wait events from Postgres 10 to 9, and we're going to continue to make improvements to try to make this visibility better. So you can kind of see that we have this big blob happening here where we have this CPU spike in green. What we can do is we can drill in on that. We can see what the statement is. So this is a select count star on a TPCC. And from there, we can drill in and see that, wow, this only occurs once in a while. So why is that going on, right? Like, why is that an issue? So this is going to be a really powerful tool. Like I said, it's going to be out on all the pieces soon. And of course, a lot of people ask me, this is great. Aurora sounds great. How do I get to it? So we'll talk about migration here in the last few minutes. So there's 4 main methods. DMS, which I'll talk about, PG dump and restore, which I won't talk about because if you know Postgres, you know those are just their standard things. Snapshot import, which was our first sort of thing from RDS Postgres, and then read replicas, which is our newer model. So for DMS, this is logical replication, so change data capture. So we can come from Postgres, Oracle, SQL Server, Maria, MySQL, any of those, and essentially what you do is you have an instance that you want to migrate from on-premise, EC2, RDS, anywhere that supports these, and you set up a DMS server, and you point it basically at that machine and at your destination, and you tell it what to do, what tables and schemas, and it's going to go do a consistent select for all those items, fill it up. That takes a while, but it's been capturing the logs, so it can basically replay those logs into your system, get all caught up, and then you can fail over, right? So this is a really good way to do it, especially if you're not on Postgres today. We introduced Snapshot Import, which is really handy for testing Aurora Postgres. You start with your application, you have Postgres, stop your application, take a snapshot, and then you tell us to import the snapshot. Once you do that, we'll convert that through our processes to Aurora Postgres, and then you can fire your application up. But as you can imagine, that takes a bit of time, and that doesn't really work for production, right? So on the other hand, if you're doing it now, we have a new feature for moving to from RDS Postgres to Aurora Postgres, where you sit there with your application, you have RDS Postgres, and you say, I would like a read replica, but I would like an Aurora read replica. And we'll say, we'll create a snapshot behind the scenes for you. We'll convert that and create an Aurora Postgres instance, right? So now you're essentially got that basic setup, and we start wall-based streaming replication between the two databases. So you're catching up after that, and once you're all caught up, you can basically stop your application, promote your Aurora SQL, and go, right? So this allows you to, we've had customers who have done like couple minute failovers from RDS Postgres to Aurora Postgres. So remember how I told you there was a few things missing from Aurora Postgres right now that are in RDS Postgres? What I tell customers, if you need those, stay on RDS Postgres for now. Wait until we have those later in the year, and then you can move pretty easily. So there's not a real risk of having a lot more data or anything like that. And with that, I'm going to wrap up. Thank you. I guess I've added this slide because I forgot it on my last one. So rate my session. Oh, Alexa's talking again. Good. She knows it's time. So yeah, thank you very much. And I have like 0 time for questions. 0, yeah. OK, so I'd be happy to take questions outside. You can come up while I'm unpacking. I just want to make sure if there's someone after me. Yes?
So this is regarding Postgres, the Linux page cache.
Yes.
If you have multiple instances on one box, it's nothing to do with
Right.
local MySQL on-premise box.
Right.
Multiple instances running on it, and is there any way you can control the Linux pages?
No.
Or how does it handle by multiple instances?
I mean, that's the challenge about using something like a Linux page cache is that it's not database specific, right? It doesn't know anything about a database. In fact, one of the challenges with running with something like Postgres in the standard fashion is that people have done stuff where they've run their application with their database. And that works fine until someone's on that box and does something that causes the file system cache to get eaten up by like some big copy or something. And then all of a sudden they're like, why did my Postgres performance go to heck? Because that's why most engines have went into their own separate page cache. But Postgres is very reliant on it for a lot of reasons, like the read aheads. There was a lot of other changes that I don't actually have in my slide deck that we actually had to make to get around the fact that there is no page cache. Like when they build indexes, for example, they bring the blocks in for the index, but they throw the index blocks away as soon as they've built them. Like they write them, they checkpoint them, but they eject them out of this ring buffer very quickly. So this doesn't matter because they're in the Linux page cache. So if you were running a benchmark and you build an index and run it, it looks fine. For us, when we first did this, we would run it and Postgres would eject all those blocks, and the benchmark ran horribly, right? Because it wasn't in cache. So there's a lot of things like that they really depend on the page cache. It's really central to the way they've done a lot of stuff. It's not a bad thing. It's just really different, and I always tell people it is one of those things to really know about Postgres. Yep. Sure.
Anything about scale out that you can talk about? Plans for scale out?
I mean, so we've announced Aurora multi-master, right? For MySQL, and we've announced that we're going to be doing it for Postgres. I've been told, and so that's part of the scale-out solution, right? Is that right now you can obviously have multiple readers, but it's one writer. In the future, we're going to have multi-writer, both in-region and cross-region. And that, I think, is right now our scale-out story. We've talked about doing sharding and other stuff, but nothing specific. I mean, we've had a few customers ask us about that, but it's not in the current.
For MySQL either.
Yeah, not at the moment. I mean, the current thing is the multi-master. Once we get that done, we'll see. Yep.
So there seems to be a lot of state that you need to keep about the blocks because you're the block manager yourself.
Yep.
Where they are replicated. Where is that stored?
So the question is, where is all that state about the blocks stored? All of it's stored in the sort of, you can think about it all being stored in the storage system. Now, one of the reasons why there was a single writer to start with is that at some point you actually have to have somebody that looks at all that and talks about the 4 of 6 quorum and figures out, where on that timeline do we have a 4 of 6, when's the last time we're good, and anything beyond that we don't actually have 4 of 6 quorum in a timeline, right? So that's done at that head node that is the writer, but it's all distributed. So essentially, and it's all like a cascading level of trees of information, right? But yeah, so the whole storage thing is highly distributed. All the repair, all the management is all broken up across the entire system. Yes?
So compared with the rate, so do you, because you don't have a page swap, so some time probably will take longer time to construct your page for the rate, for the grid blocks.
So
Do you have some special strategy to make grid faster?
So the question is, because we don't have Linux page cache, do we do any special strategies? Well, the thing is, Postgres by default reads from the shared buffers, which is like the inside the database buffers, and then only reads from the page cache secondarily, right? So we have shared buffers exactly the same way that Postgres does. So we cache all the same ways at the first level, and because our cache is larger, we basically end up with better, not worse performance, so we don't actually have to do any extra caching or anything. Because reading from the page cache is actually slower than reading from the shared buffers. Okay? Yeah. Other questions? Yes?
I had a question about the 4 out of 6 quorum.
Yeah.
So let's say one of your AZs got cut off
Yeah.
and you're behind over there. Do you just return on the read side then the stale data, or do you try
No. Well, so I mean, from our perspective, like those, we never return stale data, right? Like, so we'd always go from the, we go from the quorum side, like it is, right? And we would make repairs, and we have like, if the AZ is going to be down, you'd end up with like 6 of 6 copies in 2 AZs for a short period of time, right? Like, we'll do that, but that's like not the normal operating mode. And in many cases, like in many of our larger regions, we actually have more than 3 AZs. We just spread across 3, so we'd actually move you to like a different AZ at that point. But it's always from live data. Yeah. Okay. Yes?
We have 6 copies of data. Let's say if you have a case that's more than 6 copies of read replica.
So the copies of data are completely divorced from the number of read replicas you have, right? So that's just how many things we're writing to, right? Every read-only node, you can have 15 read-only nodes. They're reading from any of those copies, right? They're not assigned to a specific copy of data. There's no longer a binding between your head node that is like the thing you're talking to and your storage. Think of them as 2 separate things, right? It's really a clustered set of storage that you attach nodes to. Yep. Okay. Well, thank you very much. You guys have a good rest of the conference.